Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a pleasure to introduce Doug Greger. Doug specializes in parallel graph algorithms, and there's an interesting area where he works both at the SDK, API, and software reusable library development from a generic programming standpoint. And he's worked on things like parallel boost graph libraries, and he's also released many of these APIs to the world. And he also has an eye for implementing parallel graph algorithms that actually scale. So today, Doug is going to be talking about generic programming in the parallel boost graph library. With that.
All right, thank you, Kumar. So this is work I'm at the Open Systems Lab. The director of the Open Systems Laboratory is Andrew Lumsdain, and we have some students and other postdocs that have worked with us in the past. And this talk here is going to start with a very simple question of, does my clicker work? It does. So sequential programming is really simple, right? You write hello world, you crunch it through some machine, and you get beautiful graphics out. This is wonderful. Sequential programming is easy. Now, what do we do in the parallel case? Well, the standard model is single program, multiple data, right? Or we take our program, replicate it across a couple of machines, and they all work together. And so what people have been looking for years, and what I'm going to talk a little bit about in the context of generic programming parallel graph algorithms is, do we have a goal of saying, well, can we take our sequential programs and make them parallel in one way? Or is there something that is naturally both parallel and sequential, where we can take one program and run it across many machines or run it across one machine efficiently? And how do we attack this problem? And so the way we came at this problem for parallel graph algorithms is to use this paradigm of generic programming. So generic programming, as I said, it's a paradigm for building software, just like object-oriented programming is a paradigm for building software. And so we're going to discuss generic programming, what that actually is and what it means, and then move into the actual world of graphs with the Boost Graph library, which is a generic library, sequential, and how we use the generic programming approach to turn this library into this library, hopefully with a minimum of effort, and gain some understanding about the link between parallel and sequential programs in the process. So the first question we start with is, well, how do we as humans actually handle complexity? It's a tough question. When you have very large systems, of course, you can't look at the whole system and comprehend it. So what do we do as humans? Well, we break it up. We look at only smaller pieces. And then we work on individual pieces separately, get those pieces working, and then we abstract away those pieces, turn them into abstractions, ignore all the details that are lower level. We don't care about those anymore. We just think about the interfaces between those pieces. And then we compose all of these separate pieces into a working program. Right? And now what software paradigms actually do is they give us a way to express these abstractions, express the ideas of all these pieces, and then combine them. And the programming paradigms that actually do work and gain a lot of mind share are those that do a good job of building abstractions that people understand and that work well with the way people think. So you can actually look at programming languages and the history of programming language as a progression of abstractions. And we abstract in different ways at different times. So structured programming was the first real set of languages, and the big thing here is procedural abstractions. Right? You can have a little bit of code that does something when you give it a set of parameters. It always works. And once you get into that code, you don't need to look at it again. We also saw the beginnings of type abstractions and abstract data types, right? Bundling different attributes together into one sort of type that you only work on through various procedures. Object-oriented programming is very big now. And what that does is it actually says, okay, we have this notion of an object or a class of objects where we have some data in the data type, and we put inside here functions that operate on that data through some abstract interface, and we use encapsulation to hide many of the underlying details. Now, the other thing object-oriented programming did was it gave us polymorphism on the data types themselves. Right? This is virtual functions, overriding functions, etc., where you can have a subclass of a class and have different operations on the subclass than on the class. And you can treat the class itself, the base class, you can treat all of the drive types as that base class, therefore getting polymorphism. What generic programming does is it takes essentially another shoot off of the structured programming with some of the ideas of object-oriented programming. So here we're going to focus on the polymorphism itself. And we want polymorphic algorithms that work on many different kinds of data structures. And we want polymorphic data structures that work with other data types to build new data structures. Now, the key of generic programming is that we want the genericity, we want the polymorphism, but we don't want to lose efficiency in the process. Now, this is somewhat of a reaction to object-oriented programming, where we have polymorphism, but it's expensive. Virtual function calls become expensive. They inhibit optimization. They have costs on their own. So we want all the polymorphism without the loss of efficiency. And we're going to come at this from a different philosophical angle by invoking Plato. So what is Platonic idealism? So what did Plato say? Well, he said that all of reality, all this world that we live in, it's just a reflection of some kind of higher truth in the world. And he thought this higher truth was also beauty. That is, there's beauty in the abstraction. And so he said, with all these concrete objects, we see all of these chairs, and they're just reflections of the abstraction or the idea of a chair. Okay, he always liked to use the tree, right? You can go outside and see many, many different kinds of trees in the world. And some of them are real trees, as in they grow. Some of them are stylized drawings of a tree. We recognize all of these as trees because they're all just reflections of this universal abstraction of a tree. Right? And we could throw in our mathematical data structures of a tree, too. That fits somehow with the scheme. You take this idea and now apply it to software. Right? So what are the abstractions that matter? Well, we have algorithmic abstractions. So what is a quicksort? It's an algorithm. But the algorithm is just an idea. Right? It's an idea of how you can, well, sort data using partitioning and recursive steps. So when you look at what are the concrete implementations, right? What are the concrete reflections of the abstraction or the idea of the quicksort? Well, they're implementations. Pick a programming language. Write it down for specific data types. That is the link between all the concrete implementations and the idea. Now, how do we present algorithms? You look in a textbook, and we represent the abstraction. Sometimes there's C or C++ or Java code in there. But more often, if you look at the good algorithms books, it's pseudocode. Right? It's just trying to convey the idea of a sort. So what generic programming is about is starting with these concrete implementations, starting with these things in the real world that we actually use and run. And then what we try to do is move more toward the abstract. Try to build algorithms that are much more like that Platonic ideal of the quicksort. And this is an iterative process. You start with implementations, and then you're going to look at these implementations and say, well, why are these specific implementations too specific? What would make them get closer to the Platonic ideal of the implementation? And we see that, for instance, we have a sort. Say we have a sort on integers, arrays of integers. Well, why is it just a sort on integers? That's placing a very strict requirement that the user can only use integers. So we lift away this requirement. We say, well, we don't just need integers. All we need is a type for which there's a less than operator. So you take that notion of a less than operator, bundle it into something we call a concept, which is a description of an abstraction. So we can say that there are less than comparable types in the world, which are all the types that have less than operators. And we can lift our algorithm so that we have a sort that works on all less than comparable types. Keep doing this process. And eventually what you're going to end up with is a generic algorithm, which works over many, many different kinds of data types and data structures. And the two important things is, first of all, when you use this algorithm, it needs to somehow instantiate down to the same efficient algorithm you would have gotten had you written it for a integer. Right? If you're using that abstract sort with integers, it better be as fast as writing a sort with integers. This is where object-oriented programming didn't work because they don't keep as careful track of their abstractions. We can come back to that a little bit later. And somehow in this algorithm, we're getting closer to the textbook algorithm, something that really describes the higher truth, it would be what Plato would say, of the algorithm itself. that gives an understanding of how the algorithm works, and just its essential parts, none of the things that don't matter. So now we get to look at a little bit of code and start from a very trivial algorithm, sum up the integers in an array, and see how this lifting process gets us to a more generic algorithm. So simple summation of integers in an array. Very simple. I'm going to put it at our bottom as one of these concrete algorithms. And we can look at another algorithm, summing up all the float values in an array. Okay, that's another concrete algorithm. And what we want to do is we want to lift from these two concrete instances up to something that's more abstract, more generic. We can do that. We use the C++ template mechanism. So now what we're saying here is, well, we can have any type t, as long as we have an array of t's, we can add it, so long as there's a plus operator that adds two t's. Right? Continuing on, well, what if we have a sum operation that works on linked list nodes? Right? And here we have doubles stored inside a linked list. We're summing these up. Well, this is another concrete algorithm down here. It's still the same basic notion of summing up values, but now the sequence has changed. The way you look at your data has changed. Therefore, we need some new notion, some new concept. And in the standard template library, the C++ standard template library, we have this notion of iterators. It's also in many other languages, where you can walk through a data structure without knowing the underlying data structure's form. And so using this, we can write our summation algorithm to work over any sequence, whether it be an array, a list, or anything else, and sum up all of the values in there. And we get this algorithm that now generalizes all of the summation of an array, summation of list, and many other data structures that we've never even heard of. We can, of course, go further. Here's a product operation on a linked list of floats. It's the same essential idea as summation, right? You're just doing accumulation, but the operation has changed. Fair enough. Add it to our list here, and we can build yet another generic algorithm that works on iterator ranges, doing some sort of accumulation over all of them. This generic algorithm might look like this in C++ or pseudo C++. The idea is that it captures all of the ideas of accumulation in one generic algorithm. And anytime you're going to use this for a specific case, like say we want to go back and sum up the integers in an array, once we plug in the values, the C++ compiler is going to go through, optimize this code, and you'll end up with something very like our first example, the sum of integers. In fact, you should get exactly the same code from a decent compiler. That's the abstraction without efficiency, and building a generic algorithm so that it doesn't lose performance but covers a wide variety of use cases. Now, the actual process of instantiation, is, as it's called in C++, we tend to refer to this as specialization in the world of generic programming. And the idea is that anytime we do a specific use, we generate the most efficient code, meaning we generate the same code as if you didn't have all these abstractions in here. The key is that specialization works by looking at your abstractions and breaking them down into nothing. So it eliminates all of the abstractions. You can't do this with all kinds of abstractions. Virtual function abstractions, for instance, calls through function pointers, can be broken down with a lot of static analysis that often isn't done. So it's not necessarily a good candidate for an abstraction mechanism to use in the world of generic programming. So a lot of what we'll do in the world of generic programming is determine what abstractions are actually safe to use. And the list varies from language to language, sometimes from compiler to compiler. C++ templates are generally safe because there's just a substitution operation. Virtual functions are almost never safe. So lifting and specialization are kind of like two opposing forces in the world of generic programming. And they need to be essentially in balance for these actual algorithms to work well, for generic algorithms, generic libraries to work well. So as you lift to get to more generic algorithms, your specialization needs to be able to go back exactly down to the concrete algorithms you lifted from. So every time there's a path up, there needs to be a path down, and you get to the exact same place. One of the last bits on generic programming itself is the notion of algorithm specialization. So it's often the case that for specific data structures, you can implement an algorithm better because you know something about that data structure. So a really simple case here is we want to compute the circumference of a polygon, which is easy. Take any given polygon and just sum up the side lengths of all the sides. However, if you have an equilateral polygon and you know it's an equilateral polygon, well, then you need only do one multiplication to get the answer. For any equilateral polygon is a polygon, so this algorithm will work, but it's linear time, whereas this is constant time. And so what algorithm specialization is in generic programming is that you're allowed to provide multiple variants of the same algorithm. And somehow your generic programming system, your compiler, needs to select the most specific one of these to give you the best performance possible. Now I get to move into graphs. So, back to Plato. Well, there's a lot of kinds of graphs in the real world, from circuits to communication networks and so on. And all of these various kinds of graphs can be seen as just some simple abstraction of a graph. And this is where we started to build an actual graph library to say, okay, we know all of these exist. So what we need to do is build a library that works purely in the graph theoretic domain. And within the graph theoretic domain, we just need to provide some way that people can take their problems, easily map them back into graph theory so that we can operate in graph theory over a wide range of applications. So the library itself is called the Boost Graph Library. There's a book here, it's somewhat dated, that describes the evolution and design of the library itself. The most important things about the library, first of all, it's one of the biggest libraries developed with the generic programming paradigm from start to finish. And all of the algorithms are going to lift away requirements in a couple different areas. First of all, we don't care what the graph data structure actually is. That does not matter. We can work on graphs that are adjacency lists or adjacency matrices. We can work on graphs that come from existing programs, just with a minor adaptation layer. And we can even work on graphs that don't exist in memory. You can generate graphs on the fly and operate on these things. The algorithms don't care what the graph data structure is. All they care is that the graph, whatever the data structure is behind it, provides a certain simple protocol that the algorithms can use. So we also don't care how we associate properties or attributes with the vertices and edges. It doesn't matter what the mapping is, so long as when you have your domain-specific information, you can easily tell the library, okay, when you ask the question, what is the weight of a vertex? Here's how you get your answer. And we also abstract away from many of the data structures that are used in the computation of the algorithm itself, which allows users to plug in their own specialized data structures and effect slightly different algorithms in some cases, or just optimize the performance of their algorithm itself. With this library, we get this architecture where the algorithms are considered central, and these are generic graph algorithms. And then you take your graph data structures, whatever they are, come from the library. They don't have to come from the library. Plug them in through a set of graph concepts, describe the protocol of graphs. And then you take your vertex and edge properties. These are what tell you how the graph applies to your domain. Right? If you're doing a road map, then the edges might be roads. You have information about roads. But you can plug these in through what's called the property map concepts. And once you've plugged in your graph types and your properties, it'll create a new algorithm that is specialized for your particular domain and optimized for your problem domain from the generic graph algorithm. That process is, of course, automatic. So now we get to parallelism. So generic programming has been very good at taking existing algorithms and lifting them up to be more generic with respect to the various kinds of data structures that are out there. It leads to libraries that are much more flexible because they can work with your data structures, not force you into using their own data structures. So the question we ask is, can we apply the same lifting process to abstract away all of the assumptions that sequential algorithms make and actually turn them into parallel algorithms? Right? We're moving toward this initial question of, well, can we unify the notions of parallel and sequential algorithms into something that's very abstract and can be specialized down to sequential or parallel algorithms, maybe for different parallel architectures. And the idea from the start was to see how far this notion can take us and build the parallel graph library directly out of the sequential graph library. mainly to reuse code, but also to see how far this notion actually works and what kinds of algorithms can be expressed this way and what can't. So we started with the simplest graph algorithm that everyone loves, a breadth-first search. And on the left, we have the code, all of the code, from the sequential graph library that is a breadth-first search. So the code itself is relatively simple. We have a queue, and we just push our starting vertex in the queue, iterate over the queue while it's not empty, look at all of the outgoing edges of the vertex on the top of the queue. As we discover new vertices, push them into the queue, etc. It's a simple algorithm. The question is, can we parallelize this? And to check whether we parallelize this, we start to look at what kind of operations could possibly be parallelized. Or rather, we can look at all the operations in here and see how would they act if this were actually a SPIMD parallel program. So if we had data distributed among different processes. And so we think of, on the right, the abstraction of a graph, and maybe we have a data structure in mind. And we look at how this works in the sequential case. How do we enumerate the out edges in a sequential case? Well, it's relatively simple. We start at whatever vertex we have, and we walk through a linked list that gives all of the outgoing edges. What if that graph were then chopped up and distributed among different memory spaces? Right? What does that do to this operation? Well, if we have a vertex, and that vertex is local, the operation is the same. We just look up the vertex and walk through the list. If that vertex is not local, if it resides on some other process, then we would have to send a message and do a request. Of course, sending a message, doing a request, that's expensive. So we can look at this two different ways. We can either say, well, we need to have this infrastructure to pass messages and ask about edge lists. Or we can say, well, this operation here, it's the same as the sequential case, so long as we only walk the out edges of local vertices. And so what this leads us to is the notion of a distributed graph. And this is another concept, just like there's a graph concept in the graph library. And the fundamental operation here is we need to be able to enumerate the out edges of a given vertex. And that vertex needs to be local for us to do it. So we're lifting the requirements slightly. And that means that somewhere there's going to be some kind of data structure, maybe it's a distributed adjacency list, that's going to distribute along the vertices and keep all of the out edges stored with those vertices so we can iterate over them quickly from local memory. Moving on, what about the queue? So there's this queue where we push vertices into the queue, check when the queue's empty, pop vertices off. In a sequential case, this queue is just a first in, first out queue, push at the end, pop from the front. Well, we certainly don't want to have just one queue in the world of a distributed parallel system. We're going to need multiple queues because multiple people are going to be pushing and popping. And so you can imagine that we're going to distribute this queue into several different queues, all of which work together as a distributed queue. And you can push into this queue. It'll move into one of the other local queues, and you can pop from the top of your local queue. All right, so you can certainly see that the push operation invokes some kind of communication here. Now, looking at the actual distributed queue itself, there's only three operations, right? There's pop and top, which we see we can do from our local queue. There's push that can add something into the back of the queue. And the most interesting one is empty, because this is what signals termination in the sequential case. When the queue is empty, we're done. We have to look at this from the distributed queue viewpoint and say, well, what does empty actually mean for a given process? Well, a queue is only empty when its local queue is empty and everyone else's local queues are empty and there are no messages in tow. So the empty operation is really a synchronization point between all of the processors to say, well, where is the queue's full overall state? And what we end up with is the notion of a distributed queue where we have all these separate local queues. The push operation is most important because the push operation is going to decide, I have a vertex to push, where does it go? Who gets that vertex? And the only answer we can actually use here is that if people are going to pull off their local queues, then when you're pushing onto a queue, it better pass it over to the processor that owns that queue so that this operation works. So we have some coordination between data structures here, where we say that the queue is going to make sure that the appropriate processors get the right vertices so that they can always traverse their local vertices here. There's one last set of operations inside the breadth-first search, which is this notion of the color of a vertex. So we use white for vertices we've never seen, gray for vertices we've seen but we haven't processed yet, and black for vertices that are already finished. And throughout the algorithm, we're going to query the color of target vertices when we're doing the breadth-first search, and based on that, decide whether to push into the queue or whether not to push into the queue. In the world of the BGL, you can imagine there's some virtual table here that maps from vertices to the colors of those vertices. And in a world of distributed memory computation, parallel computation, you're going to need to divide this structure up into several different structures. Now again, we're going to use a convention that if a processor owns a vertex, it's also going to own its color. So we keep all information locally. And these colors are in different memory spaces. We might have these ghost cells here that keep old copies, or potentially old copies of the colors of vertices on other processors. And we tie this together with the distributed property map operation, the distributed property map data structure. And this is actually a class of data structures because it's a concept. It's not a real type. But there's only two operations here. We need to be able to set the value of a vertex or edge or get the value of a vertex or edge. Now, both of these imply communication. A put operation to set the value implies sending a message across the wire and that person deciding, well, how is he going to handle puts from multiple processors at the same time. Inside this distributed property map notion, we're going to have these ghost cells automatically handled. And the get operation that retrieves a value, well, that may need to do, in some cases, depending on the algorithm, it may need to go across the wire and ask for a value. It may be able to synthesize a safe value locally. So we've talked about three main kinds of distributed data structure concepts that are here. We've got property maps, the distributed graphs, and distributed queues. And all of those are necessary to make that breadth-first search algorithm we had work like a parallel algorithm. So this is what the actual declaration of breadth-first search looks like in the sequential graph library. It's parameterized on the graph, so it works with any graph data structure. It's parameterized on the queue, so it works with any queue. Typically you use the first in, first out queue, but not always. It's parameterized on the color map, which is how we associate the colors with the vertices. And there's this other parameter, probably won't talk about much, that is a visitor that gives you events each time something interesting happens during the breadth-first search. That's used by users to customize the algorithm as they go along. So if we want a parallel algorithm out of this sequential algorithm, we need to plug in all of those distributed data structures that we found from studying the algorithm itself, which means we need to plug in a distributed graph instead of a local sequential graph here. We need to plug in a distributed queue that knows how to do pushes that send messages across the wire and knows how to synchronize all of the queues. And we need a distributed color map that knows how to do put operations across all of the various processors and synchronize data access to the properties of distributed graph. Once we plug all of these into the sequential algorithm, we end up with the parallel algorithm. It's a somewhat strange result because the sequential implementation we had that's been around for years and years is just developed for data structure independence, also has a distributed memory parallel algorithm in it. You just need to give it the right data structures. So from this, we decided on what the parallel BGL's architecture actually would be as a generic library. We took the BGL architecture itself, and we found that we could wrap all the parallel components around the sequential components. So we take the high-performance sequential components we have, wrap another layer around it that does communication across processes, and we get massive reuse of code. For instance, the breadth-first search algorithm does not change. We just drop in the right data structures. And so our parallel graph algorithms either are or use directly all the sequential graph algorithms. We wrap those around. And then we take, for instance, our distributed graph data structures, all have the local data structures built in, and we can plug those into our parallel graph algorithms, take our local properties that have information about local vertices and edges, distribute them to give the coordination across all the various processors, plug that into the parallel algorithm. And finally, there's a set of abstractions, which we call the process groups, that abstract the notion of communication among all of your processes. And so we tend to use MPI, the message passing interface, for large-scale distributed computation. And but we can also do threads or other systems that know how to pass messages, essentially. And we plug this communication abstraction in throughout all of the distributed graph data structures, the distributed property maps, and the distributed algorithms themselves to affect parallel graph algorithms that are set up for a particular environment and are optimized for a particular environment. So the process groups themselves, they actually use a message passing style internally with active messages. That's the basic model for computation. And we divide up most computations into BSP-like supersteps, BSP being the bulk synchronous parallel model. Now, the strict bulk synchronous parallel model is a bad idea because you can't keep your memory usage to something usable. However, the notion of supersteps makes algorithm design much, much simpler. And a lot of the graph algorithms we've found have very natural superstep boundaries where we can do computation. So one of the most important things about the process group concepts themselves is they have explicit support for distributed data structures, like the distributed queues, like the distributed property maps. Because within any particular algorithm, any parallel algorithm, you tend to have many, many different distributed data structures. Sometimes the algorithm knows about these, sometimes it doesn't, because the user might have their own that they've stuck in through a visitor. So the process groups actually tie together all these distributed data structures so they all synchronize together within superstep boundaries. That actually gives us a very simple model where the parallel graph algorithms don't need to know about all this extra work that's going on. Right? Well, that's why a sequential algorithm was also parallel. And it means that users get a lot of flexibility in using the parallel graph algorithms and customizing them for their own usage scenarios. So look at a little bit more code. If you're actually using the library, a lot of these pieces are hidden from you. So when you want to go build something, say you want to build your roadmap and it looks something like this, what do you need to do? You need to have the abstract structure of the graph. And you need to tell the library how that structure is going to be laid out in memory, what data structures it should use, etc. It's all your choice. And then you add in your domain-specific information that say, well, what is a vertex? A vertex is a city that maybe has a name and a distance from some source. And what is an edge? Well, maybe it's a highway with a name and a length in miles of the highway. And then you build your graph data type. So you could create your own data types if you'd like to create your own data structures. That's fine. The library also provides one it calls adjacency list, which is the Swiss Army knife of graph data structures. When you're using the adjacency list, you essentially decide how it's going to store things at every single level of the hierarchy. So the first parameter here is when you have a vertex, there's a set of out edges. How's that stored? We're telling the library, use a linked list for the storage. That'll give us fast insertion and removal. And when we move to the vertices, we say, well, how are these vertices going to be stored? Well, the vertices are going to be distributed across processors. To communicate among all of these processors, we're going to use MPI. That's our process group. And each processor locally is going to store these vertices in a vector, dynamically sized array. Had we left off distributed S and MPI process group and just used vec-S, well, that would say store all the vertices in a vector. So that would be a local graph. This is where the distribution enters. And we say, well, how are our edges? Are they directed edges? Are they directed edges with backlinks? In this case, we're going to use undirected edges, so there's no directedness to them at all. It'll be stored in both places. And then we add our domain-specific information saying that with each vertex, there is a city, and with each edge, there is a highway structure. And these are going to be stored along with the vertices wherever they are in the actual program. So the hardest part of a lot of computations in graphs is actually getting these graphs built and distributed properly. We've run into this trouble with many different things. The basic problem is that your graph is much bigger than memory, always. And so you need to distribute the graph on the fly from usually many different input sources. And so one of the things the Parallel BGL tries to do well is simplify this task. And in fact, we've simplified it down to basically this. these lines of code where you have some input stream, and everyone has a different input stream, presumably. Pull in your data about edges from that input stream, and then add those edges to your graph. And what's happening behind the scenes here, there's actually a lot of work going on. There's a mapping that you provide from the vertex properties, as in every vertex is a city, to some kind of unique identifier for that name. So for city, it could be the name of that city, including its state information. If we were talking about a web graph, that would be a URL for a document. Whatever that unique thing is. And once you've identified this, the parallel BGL itself is going to keep track of that mapping in both directions so that you can talk in terms of the name of this entity. And it will manage all of the distribution behind the scenes. By default, it uses a very foolish randomized distribution strategy. However, for any serious application, you plug in your own strategy for distribution that's based on whatever heuristics are useful. We know some of the heuristics for web graphs. The heuristics vary from domain to domain so much that we have to leave this up to the user. So once we've built our roadmap, which is relatively simple, say we want to run some operations on it. We want to compute the shortest paths from, well, we're starting at Bloomington here, out to everyone else on the graph. Simple shortest paths computation. So first thing to do is we want to find the vertex descriptor associated with Bloomington. Vertex descriptor is like the internal name of a vertex inside the graph library. It's how we refer to vertices. And then the shortest paths computation itself is relatively simple. It's going to be Dijkstra-based, starting from Bloomington. And then we tell the algorithm where it should store information about the distances from the source to these other locations. And what we say here is, well, there's a city structure associated with every vertex. So store it in the distance member of that city structure. And how do we decide what it actually means to traverse an edge, what the weight of an edge is within the Dijkstra's algorithm? Well, we know that every edge is a highway, so we pull out the length field of that highway. If we want to do something differently, like finding the fastest path instead of the shortest path, we could just drop in another kind of property map that takes into account the speed limit and in addition to the length of the highway. It'd be relatively simple. And at the end, we print the results. Now, the most important part of this code from all the last 3 slides is that it's sequential and it's parallel. It doesn't matter which. The only part that doesn't work well in parallel is this step, because your output's going to get mangled when you try to print to the consoles of all your processes. But the idea is that this original type def that we created here says that this is a distributed graph. And because of that, all of the algorithms in the parallel BGL act as parallel graph algorithms. It uses the parallel variants of them if it's a variant, or if it's like breadth first search and the sequential version is also the parallel algorithm, you'll get the parallel algorithm out of it. Had we changed this type def to take away the distributed S and make it a local graph, everything would work the same, and you'd be using the sequential algorithms. So we're really trying to get to the point where you can write an algorithm and it's either parallel or it's sequential based on what data types you plug into it. So we've implemented quite a few algorithms in the parallel BGL. Well, maybe not quite a few. And we found that some of them work wonderfully, like breadth first search, where you can just drop in your parallel data structures. And other algorithms fall flat on their face, and you need to take a completely different approach to parallelism. Some algorithms that do work, a lot of the single source shortest paths algorithms work well because they're based on breadth first search. Some other algorithms work well. Let's see. Well, PageRank does. Connecting components almost does. Force-directed layout, interestingly enough, does work. Other algorithms that tend to be based on depth first search, which is inherently not parallelizable, those sequential algorithms fall over, and we need to do completely different implementations of things like strongly connected components and so on. But we have a decent suite of algorithms. We're always trying to improve this and study the performance of these guys. So I like to drop back to this issue. I came to it in the beginning where I said object-oriented programming introduces abstractions that are slow, or that imply that there is going to be poor performance. And there's this myth mostly in the high-performance computing community that says that any kind of abstraction is going to slow you down. Therefore, you should write the lowest level, nastiest Fortran code you possibly can. And we've been working to try to change this myth, or at least see that it is truly a myth. And one of the things we did with the Boost Graph library, this is the sequential library itself, is there's a bunch of sparse matrix ordering routines written in this graph library. They're all very generic. They work on any data structures, etc. And so we compared them with some highly tuned Fortran codes that you can find out in lib for sparse matrix ordering. And what happened is, well, they ended up performing on par with these routines. They're 1% faster in some cases. We're 1% faster in other cases. But the point is that the performance curves of these are exactly the same. So it is possible, even with a very high-level, very abstract library like the Boost Graph library that works on a huge number of data types, that the C++ compiler can generate very efficient code out of that. And we've seen this in a lot of other generic C++ libraries. We've heard of Blitz and Puma and MTL are things more in the linear algebra domain, where they've gotten Fortran level performance out of very generic libraries. And these libraries, of course, work with so many other data types that they fit better into existing programming systems. Now, there is a reality that there are many high-level libraries that don't give you Fortran level performance. Well, they give you 1,000 times Fortran performance in the wrong direction. And what happens here is that if you use the wrong abstractions, you can get poor performance. Right? So we need to only use the abstractions the compiler can eliminate. We got an interesting lesson in this where we went out and found one of the only other free parallel graph libraries in the world. Actually, as far as I know, there's only 2 free parallel graph libraries. One's ours, and here's the other one. It's called CGM Graph. And we looked at their performance results, and they were doing connected components on relatively small graphs, and they gave a performance curve that was this. And we were able to duplicate that. And we ran ours, and we were like 17 to 30 times faster than they were. I believe we could be down here still. But the point is, we tried to dig into this because they were implementing essentially the same algorithms. It was C++ over MPI, same basic algorithms, same generally basic approach, and they're based on coarse-grained multi-computer model, where we were BSP-like at the time. And we're trying to decide, well, where does this performance problem actually lie? Because it's obviously not in the lower layers, it's in the library. And we found that they weren't managing their abstractions properly. They have virtual function calls. They have lots of heap allocations that aren't necessary. And essentially what they'd done is they'd built a simple data structure as their model, and then they implemented their algorithms using the object-oriented polymorphism style. And that lost them the 30x performance. This is the same kind of performance problems we see when we compare against Java libraries, where you have virtual function calls everywhere, indirect calls, and we see 30 or 40x speedups in that case. Now, interestingly, the parallel BGL is a much more generic library. It actually works across a larger class of graph algorithms than CGM Graph could. So it's more abstract, yet more efficient at the same time. Now, what we don't know, I can't answer for you, is whether someone can go in and build something on MPI that's down here because we made a mistake in our abstractions. It could happen. So just looking really quickly at a couple other algorithms, performance results here. There's an algorithm called delta stepping for shortest paths. And what it is, it's a single source shortest paths. It's roughly Dijkstra-like with a parallel queue. And we ran this on error-to-training graphs on a relatively small cluster. It's about 100 nodes. And performance curves were getting decent, strong scaling as we add more vertices and scale the size of the problem. We get decent weak scaling as well. So these are graphs with billion vertices, couple billion edges. We'd like to go much larger for shortest paths, but we haven't gotten there yet. We can look at it as a slightly different metric, as in how many vertices per second can we actually process on these graphs. And from here, as we increase the size of the graph, we process slightly fewer vertices per second because this is not actually a linear algorithm. But they were getting decent performance across all different graph sizes. within our cluster environment. And this is just a simple commodity cluster. I talked a lot about data abstraction and how the parallel BGL works on multiple data structures. So this actually matters to users because they have trade-offs to make in what data structures to use. And we want them to make those trade-offs, not us. We'll support everything. So here we're actually doing something from the DIMAX Shortest Paths Challenge, where we're doing shortest paths computations on the USA roadmap. And here we want to do the exact same computation, except switching off between a compressed sparse row representation and the adjacency list representation. Both are part of the Boost Graph library. And we see that with compressed sparse row, we're getting about, I think the runtime is about half here. So we're getting a 2x speed up, moving from the adjacency list to the compressed sparse row. Of course, the compressed sparse row graph is much, much more tightly packed into memory than an adjacency list. So we can actually run on many fewer processors, so we're using less memory. But there's more trade-offs than that. So compressed sparse row is certainly faster. You get better cache locality. You put more into memory than an adjacency list. But an adjacency list is much easier to use for the users. So the way we expect users to do things is, well, they'll probably work in adjacency lists to get their applications running. And then if it's worth the performance hit and the time spent, they can convert from one data structure to another. Most of their program will remain exactly the same. All the algorithms will be the same algorithms, but we'll get this extra performance from improved memory locality just by changing the data structures. Very last bit here. Very good generic libraries can be composed. And by composed, I mean you can take two different libraries independently developed, possibly even for different domains, and use them together in some way, twist them together into your application domain. So we really want to do this because when a library is composable with other libraries, it means that you can now take ideas from one domain and apply them directly in another domain, which may be your application domain, or it may be related through some third application to the domain that you're interested in. And so we did a case study here in parallel graph eigensolvers. So the eigenvectors of graphs provide information about various, depending on which eigenvectors you're looking at. You get information about different characteristics of the graph. For instance, connectivity is one of them. And so there's this other library out in the world called the Iterative Eigensolver Template Library. So it's a free C++ library developed at the University of Zurich. And it works in the world of linear algebra. And we said, well, we know that a graph can be viewed as a matrix. Right? You can view a graph as its adjacency matrix. So can we compose the parallel BGL, which already existed at that time, with the IETL developed by someone else, and actually compute the eigenvectors of parallel graphs using the IETL without rewriting any of the algorithms in the IETL or rewriting our own data structures? So both of these are generic libraries. And we were actually able to develop a set of thin adapters, as in there are a couple hundred lines of code, that make the existing parallel BGL graphs act like matrices. Like they could be 0-1 matrices if you're just looking at the structure of the graph, or they could be weighted matrices if you have edge weights in there, whichever you'd like. And the idea is that we just write the thin adapter layer where the few core linear algebra-like operations that the IETL needs to be able to do its solving of eigenvectors can be applied directly to a parallel BGL graph. So it's not a conversion of data structures. It's a view on a data structure from the perspective of a different domain. And we took the parallel BGL property maps, which associate information with each of the vertices or the edges in the graph. And when you're associating information with each of those, you can view this as like another vector of information in a linear algebra sense. And what we get is an architecture like this, where we have the PBGL on one side, and it plugs into a set of adapters here that map from the world of graph theory, actually parallel graphs, but it's just graph theory, into the world of linear algebra. And through these adapters, which are very lightweight entities, like I said, we can plug those directly into the generic algorithms of the IETL. And what we actually get is, using a parallel library here and a sequential library here, We plug this in, and we effect a parallel graph eigensolver out of these two libraries. And there's a couple scalability numbers. These aren't terribly interesting, other than they move generally in the correct direction. We'd like to do a lot more studies in this area because there's a lot of work that goes on in building good libraries for very specific domains. But as soon as we have the ability to plug libraries together from many different domains, we're going to get much more cross-domain fertilization. And with generic libraries, it becomes very easy to plug one library into another and to plug many libraries together. And we could have another parallel graph library over here. As long as it meets the ideas and the interfaces of the parallel boost graph library, it will automatically work within the IETL. So you can do essentially graph eigenvectors on a third-party library that knows nothing about even generic programming. So try to wrap things up here. Generic programming itself is a methodology for building software libraries. So there's a dual focus in generic programming. First of all, the focus is on reusability. We want libraries that are flexible, that work with many different data types, that can be adapted easily to your program instead of adapting your program to the library. And second of all, we focus on performance. The abstractions that we put into the library to get this reusability, to get this genericity, cannot affect performance. Otherwise, the library is going to be much less useful. We found that this is applicable to parallelizing existing sequential algorithms. In some cases, it isn't always applicable. So the parallel graph library itself is a generic parallel graph library. It's generic with respect to the graph data structures, properties on the graphs, and the underlying communication medium that's used to coordinate different processors. It has a suite of distributed memory parallel graph algorithms. We haven't looked at shared very much. And it's efficient, more efficient than what we've seen. We don't know what the baseline is. And scalable, at least out to the hundreds of processors that we have available to us now. Who knows when we go to much larger systems. If you're interested in the parallel BGL, of course, you can talk to me. There's a web page out here with more information, publications, etc. Are there any questions?
So how does dynamic graphs work? Right? Like the whole partitioning of vertices
Yes.
works great when your graph is static. But if your graph is built on the fly.
Well, if the graph is built on the fly, then the way that you add new vertices or edges into the system, you need to know where they go. So the way that we do our distribution is not through a static distribution of distribute it, run a partitioning algorithm, and then move the graph. What we do is we build a hashing function that encodes the appropriate distribution. Essentially, often we use a perfect hashing function based on a known static distribution. That'll also give you information about distribution of incoming vertices. If things become unbalanced, of course, you need to recompute your hashing function to do something better. But the idea is by using a hashing function, it usually takes much less memory and less computation to tell where things are going to go, and you can evolve in memory. It may not be the evolution, but it's usually a workable evolution.
Is there already APIs in your library or in the Boost graphic library to build graphs dynamically?
Yes. Yes.
I had a question.
Sure.
The mic here. The mic is here. One of the first slides of your presentation, you talked about, and later you touched on that point, the virtual functions and
Yep.
how they impact performance negatively and all that.
Sure.
But it seemed that you were presenting your approach as some form, a way to address that problem.
Mm-hmm.
And I don't know, just the way I see it is they're kind of different problems. They're different types of abstraction. One is more runtime. The other one is more compile time, where you have the opportunity to do static analysis. So of course, you're going to get
Sure.
better optimization opportunities there because you have this static. Everything is static, right? So I don't know if you intend to propose as or to present as a solution to that problem, or you make that distinction of.
So the distinction we make is that with object-oriented programming, well, I shouldn't say all, but nearly all object-oriented languages out there tie the notion of tie polymorphism to runtime polymorphism. We don't like to make that distinction. We like to look at just polymorphism. And in the languages that we typically use, like C++, we use the polymorphic mechanisms that evaluate it at compile time and therefore give you better performance. Now, there's nothing that prevents those same mechanisms from being implemented at runtime. And we've seen this with the C# and the .NET virtual machine, where the generics can be executed at runtime. They can also be instantiated at runtime. They could be instantiated earlier, if need be. So I think one of the things we're looking at is with virtual functions and object-oriented programming, runtime has come with the polymorphism. We'd really like to teach and make this compile time decision something that's programmer controlled or controlled by optimizers, as opposed to being fundamental in the ideas.
So you could say that there's in a sense a workaround for problems with the C++ language and C++ compilers. So there are languages with stronger type systems that give the compiler more information about what's going on. And
sure.
There are, I mean, in programming language research, there are well-known techniques to be able to do type analysis, data flow analysis, and figure out, for example, if for a specific call invocation, if only one specific type could ever flow there,
sure.
then you can do the optimization of the compiler. And I think there are religious wars fought over this. I think
Sure.
there's something to be said. One thing to be said for the other side is that compilers have an easier time of avoiding code bloat. So, for example, sometimes you actually don't want to instantiate specifically each type.
Sure.
Sometimes if you can determine that this is actually not going to be the inner loop, especially if you're doing kind of runtime optimization as you're going, sometimes it's actually more efficient just to have one copy of the code that maybe has more instructions, but is more likely to stay in the instruction cache
sure.
than to specialize everything.
Right. Well, that would be another reason to tease apart the notion of polymorphism from the notion of whether is it runtime or is it compile time. And most OO languages don't give you that choice. C++ also doesn't give you that choice, except manually you can convert a template into something that is more dynamically dispatched if you want. Regarding compiler optimizations, there are optimizations that can devirtualize functions. And
Except it's hard in C++.
it's hard in C++, and the concern is that when you're building up many abstractions, you're building up deep abstractions because you're mapping through domains, etc. At some point you overload the compiler's ability, regardless of how smart the compiler is. You're going to overload its ability, and then you get this drop off where your performance is fine, and then it tanks.
And you have that with both sides of the religious war.
Yes, you do.
Functions, maybe the optimizations stop working. With this, maybe you start doing so many specializations that code load just goes out.
Exactly. And I think the answer is to really tease this out. It's not an issue of. It's an issue that really needs programmer control,
But
and
perhaps
probably
we
needs.
all work toward a holy grail where the whole thing is unified, and we find exactly the right trade-off to give the compiler the information to make the right decision without the programmer having to.
That's possible. Part of doing that is finding a way to express polymorphism in a way that's amenable to both static optimization and dynamic compilation. And I don't know that we have that yet. Get into the world of parametric polymorphism. That seems like the right place to be because you can do substitution. Templates certainly aren't the right answer because you can't compile those. So yeah, we need something new.
I was wondering during your presentation, it seems that you tested all these algorithms with one type of cluster, which seems a homogeneous cluster with message passing paradigms and all. How much you explored extending your approach to other types with heterogeneous clusters or shared memory or whatever?
We've done a little exploration into the world of more into shared memory and threads, seeing how the abstractions hold up in that place. And what we found is that, of course, you can treat threads like a message passing system if you want, but it's not the most efficient way to do things. So what we found is that what you want to do is at the very top level, do treat threads like a message passing system. And you build a process group that's threading. It does all of its communication through shared memory, etc. It's still doing message passing. Then the next step is you start specializing the parts of the library where you can get big performance improvements. So for example, if you have one of these property maps where you have information about all the various, some attribute for all the vertices in a graph. Now, a distributed property map is really expensive. It has ghost cells in it. It does communication over these ghost cells. In shared memory, of course, you could just lay out the entire thing in one big shared memory segment and now start using locks or atomic operations. And so the way we deal with this is not to build new algorithms. It's to provide a specialized version of the distributed property map data structure that only applies to these threaded process groups where things live in shared memory. And then you're putting your get operations now map down to atomic. So now they map down to something with locks. But the rest of the algorithm still does its message passing. It still uses the idea of process groups. So the idea is you can very quickly move from one communication medium to another and then only specialize the parts where performance really matters.
How does that work when you have a cluster of machines where you have distributed processing at the cluster level, right? But you have the parallel processing with multiple processors
Sure.
for each individual machine. Don't you need two different approaches?
We would need two levels for that, yeah, which we have not done this. The viewpoint is that we would build essentially a composed process group that knows what are local process numbers and what aren't local process numbers, and do the local optimizations with atomics within one compute node, and then fall back to message passing. There's certainly going to be some overhead in making the decision of which to do there, but it's going to be much better than the overhead of including extra ghost cells, et cetera, et cetera.
At the current state, the level of abstraction you built in the library doesn't support that. That's what you're saying?
It does not support that case, no.
Okay.
What's the network usage during the computation? So it seems to be somehow it's very challenging, right? So you don't batch you send too many messages around. So because this you have different distributed, it's too fine granularity of the.
So we do batch messages. The process group abstraction is actually a big level step above MPI. And the process, well, where we have an MPI process group, for instance, we do batch together messages.
So when you do get all this distributed data structure, they do somehow internally they put the message together and then.
Yes, yes. So the view from the programmer side, writing an algorithm using this, is that you have fine-grained messages. But the actual implementation is going to batch messages as appropriate for the network's bandwidth and latency characteristics. In some cases, you do need the semantics of this has to go out now because I need to wait for a reply.
Yeah.
And there's a special channel, well, it's called out-of-band messaging that we'll go over quickly. It should only be used sparingly. And in fact, in the library, we only use it when the user has done something that requires an immediate answer. We'll never do it internally on our own because it's not efficient.
Sometimes it is synchronization.
Yes, sometimes need it for synchronization. Yeah.
So, can you comment on like all the number? You have a couple of graphs that showed performance improvements, and I can imagine that when you build the SDK or when you build the application, you start with you go for correctness. You go
Yep.
with the least specialized version, something that already works on 10 other different data structures.
Right.
And once you have your data structures plugged in there, and they're sort of sane, then you get some correct answer first.
Yes.
Then you move. So in the graphs, the first question is how much effort does it take to go from the first curve, which you're not too proud of, to the last one where you're like, okay, I've done enough, I've got enough speed up, and then it's time to make that slide and put it out there. How much is there? And is your only trick specialization, or is it how do you go about tuning like PBGL that's template based for performance?
So, how long does it take varies so much from algorithm to algorithm. So, some things, the delta stepping algorithm I showed, we did this because we wanted to compare against one of Cray's exotic architectures, and it took a day to implement in parallel BGL and a day to tune it. And then we've been using those numbers since then. there's usually two tricks that go into optimizing. First is algorithmic optimizations. It's the first thing you do because they're the most generic and they work across a wide variety of platforms. And then the second step is we start specializing down for maybe it's the architecture, maybe it's the particular data structure, whatever. And so we'll add those specializations in. And usually, in the worst case, this is sort of a process that comes from both ends, where you're doing algorithmic optimizations up here, and sometimes you just have to build a quick and dirty prototype that has no templates in it and is not generic to see how well can I actually do on my data structures. And then you convert those into specializations and lift those specializations up to the point where it gives you the performance benefit and the most genericity possible. So we see it as sort of a build the generic first and then integrate other ideas from concrete implementations at the appropriate level to get the right optimizations. And we can accrue these things, many of them, over time in the framework.
So generic programming just gives you a good initialization point, but there's still work that usually goes in, especially through specialization or trying to change the algorithm itself to get the final.
Yeah, there's always work in specialization. And the way generic libraries usually evolve is you have the most generic version, and then as you find new ideas that only work at specific points, you drop them into the right part, and you end up with really a hierarchy of algorithms that all have the same name. And there's just a dispatching process that picks the best one based on the properties of the data structures you're using at that particular point in time. All right. Well, thank you.